Hello everyone, today I'm going to talk about the Fulkerson algorithm for max flow, what it's used for, how it works, and analyze its complexity. So first and foremost, what problem does it solve? As we said, it's for max flow problems. So it's to find maximum flow in a flow network from a single source S to a single sink, also called terminal, T. We can use this algorithm to solve problems in many different situations, like for example freight. A company might want to know what's the maximum number of trucks they can send from one place to another, according to a road map, where roads have different capacities. So to find the maximum flow using the algorithm, we will need a simple directed graph to represent the flow network. As mentioned before, it has to have one single source, S, and one single sink, T. And all of the edges have to have non-negative capacity. You can think of the edges as pipes or roads through which material can flow, and of the vertices as junctions. We will also be making a residual graph, in which the only edges it shares with the flow network are those whose flow can still be increased. The capacity of an edge in the residual graph is equal to the capacity of an edge, the same edge, in the flow network minus the flow going through that edge. In order to make that decrease, we will add reverse edges. This is called cancellation. The capacity of the reverse edge will be increased every time we find a new flow flowing through it. And in this residual graph, we will look for augmenting paths, which are simple paths from the source to the sink, and we will try to find the residual capacity, which is the smallest capacity of all the edges along P. So all put together, we will make the residual graph, search augmenting paths in it, for each of them find the residual capacity and add it to the maximum flow.
While there still exists an augmenting path P in the residual graph, find the residual capacity, and add it to the maximum flow. Then for each edge in the path, decrease the capacity by the residual capacity if it's one of the original edges. If it's one of the return edges, then increase it by the residual capacity. Let's see this algorithm in action now, with this example. We first set all flow to 0, and in the upper graph, the numerator shows the flow and the denominator shows the capacity. Then we go looking for an augmenting path. For example, this one, SACT. We look at the residual graph and try to find the residual capacity, which is 8. We add it to the maximum flow, and then we update the flow in the upper graph. Now we update the residual graph by adding back edges of capacity 8. First SA, then AC, then CT. And we go looking for another augmenting path. For example, SBDT. Again, we look in the residual graph for the residual capacity, which is 3, add it to the maximum flow, and update the flows in the flow network. And then we do the same as we did before, we add the back edges to every edge in the path, only this time with capacity 3. SB, BD, DT. And we go looking for yet another augmenting path, this time SABCT. We look for the residual capacity in the residual graph, which is 1. We update the maximum flow and the flow in the flow network. Then we update the residual graph, still the same way, adding back edges of 1 and updating the capacity for each edge. And we go looking for another augmenting path. Only this time we find none. As you can see with the grey edges, there is no possible way to get to t from S. So the algorithm has terminated and is returning the value 12 for the maximum flow. Finally, let's take a look at the complexity of the algorithm. The flow is at least increased by 1 at every iteration because we are dealing with integers. So the while loop is repeated fm times at most, where fm is the maximum flow. Within the loop, we find augmentation paths, which run in time O of e, where e is the number of edges. We also do operations on value to update the maximum flow and the capacities on the edges, which run in time O1. So for each iteration, it runs in time O of e. This means that all in all, this algorithm runs in time O of e times fm. So that was it about the basic implementation of the Ford-Fulkerson algorithm for max flow. I hope it helped, or that it was somewhat clear, and have a good day.